ever wondered how scientists map out the Earth's hidden layers? It's not just digging holes, you know?
Nope, it's way more high-tech than that.
We're talking about seismic waves, and today we're exploring a clever way to analyze them using artificial intelligence.
Exactly, using a convolutional neural network to analyze dispersion curves.
So this paper is all about using AI to improve the efficiency and accuracy of seismic imaging. Sounds pretty cool, right? So let's start with the basics. What's ambient noise tomography?
It's like listening to the Earth's heartbeat. We use the constant vibrations from things like traffic and ocean waves to create images of the subsurface.
So it's not just about big earthquakes.
No, we can get a lot of information from everyday vibrations.
Right, but with more sensors, you get a ton of data, right?
Exactly. A massive increase in data volume makes it hard to sort through everything.
So how do you deal with that?
That's where the convolutional neural network comes in. It helps us quickly evaluate the quality of the data.
So the CNN is like a super-powered filter?
You could say that. It learns to identify high-quality dispersion curves, saving a lot of time and effort.
And how accurate is it?
Pretty darn accurate. The model's results were only about 10% different from manual screening. That's pretty good, huh?
So once you've got your high-quality data, what's next?
We need to understand what factors affect the quality of those dispersion curves.
Like what?
Things like the distance between the sensors.
So the further apart the sensors are, the better the data?
Generally, yes. Low-frequency waves travel further, and those are the ones we need for high-quality images.
Makes sense. So how do they figure out the optimal distance?
They use statistical analysis to find the sweet spot. They found that distances over 8 kilometers gave the best results.
And how did they predict the loss rate for different regions?
They used a Monte Carlo simulation. It's like running thousands of virtual experiments to see how different sensor arrangements would perform.
So it's a way to predict the best places to put the sensors?
Exactly. They created a map showing the ideal locations for optimal data collection.
So they ended up with a map showing where to put sensors for the best results?
Yes, a contour map showing the inherent loss rate for different regions.
And what did that map tell them?
It showed that straight lines longer than 15 kilometers were needed to keep the loss rate below 0.5. Interesting.
So what does all this mean for seismic imaging?
It means we can get better, more efficient images of the Earth's subsurface.
And what are the practical applications of this?
It helps us understand geological structures, locate resources, and even assess earthquake hazards.
Are there any limitations to this study?
Yes, the results are specific to the instruments and area used in the study. More research is needed to see how these findings apply to other regions and sensor types.
So it's a starting point for more research?
Exactly. This study provides a framework for optimizing seismic data collection and analysis.
Let's recap the main points. First, the CNN model is a reliable tool for quickly selecting high-quality dispersion curves.
Second, the distance between sensors is a major factor affecting data quality.
And third, Monte Carlo simulations can help predict the best sensor placement for optimal results. Right? This research has implications beyond just seismic imaging, right?
Absolutely. The techniques used here could be applied to other fields dealing with large datasets and complex patterns.
Like what?
Anything from medical imaging to environmental monitoring.
So this paper shows how AI can significantly improve the efficiency and accuracy of seismic imaging.
It's a great example of how AI can be used to solve real-world problems in the geosciences.
That was a great discussion. Thanks for sharing your expertise.